Section 4.3 is on page 267, talks about derivatives of exponential functions. And it turns out derivative of e to the x is simply e to the x. You get it back. And if you take a derivative with respect to x of e to some function u, that's e to the u times the derivative of u, basically the chain rule. Now, no big secret, the chain rule applies on every derivative that you take from all of these sections. So, if I look at page 273, and I start with problem number 2. If I want to take a derivative, now you want to be cautious for that. The only reason I'm doing that, because this does come up every now and then. 5e to the 1 is an actual number. E is 2.71, and a derivative of a constant is always 0. E to the 1 is a number, e to the second power is a number, e to the fifth power is a number. E to the x is a function. It is varying. If I want to take a derivative of e to the negative 3x to the fourth, when I take y prime, that is e to the negative 3x to the fourth. So derivative of an exponential is the exponential with the base of e times the derivative of this, which is negative 12x cubed by the chain rule. And if you clean it up, the back of the book will have it written slightly different. Negative 12x cubed e to the negative x to the fourth. And if I wanted to take a derivative of number 8, that's 8. Derivative of an exponential is the exponential times derivative of radical x. And by now, you really took the derivative of that too many times. When you take a derivative of this, that would be bring the power down, subtract 1 from the power. And since we take a derivative of that too many times, it's worth memorizing the derivative of square root, specifically square root, nothing else, is 1 over twice the radical of x. So g prime would be 4 e to the radical x over radical x. And if I take a derivative of number 16, y prime is the product rule, 2x times e to the x plus x squared, derivative of e to the x is e to the x, minus the product rule, 2 derivative of the first times the second, plus the first times derivative of the second, and derivative of 2 times e to the x is 2e to the x. Or, I could factor an e to the x out. That would be x squared minus 2x plus 2. And so you could clean that up. Or I could take a derivative of y and say that is derivative of the first times the second minus the first derivative of the second is 2x minus 2. You could clean that up by factoring e to the x out. That would be x squared minus 2x plus 2 minus 2x plus 2. And that would be e to the x times x squared minus 4x. That's what you will find in the back of the book instead of this mess. On number 22, if I wanted to find an equation of the tangent line, here's the point. I'll say y minus y1 equal m into x minus x1. All what I need to do is find the slope of the line, which is the derivative. Derivative of an exponential is the exponential, times the derivative of the exponent, which is 3x squared minus 4 at negative 1. I'm looking at e to the third power, negative 1 plus 3, times a negative 1 in there. 3 minus 4 is a negative 1, so that's negative e to the third. And there it is. Something that comes up a lot, you need to solve the equation for x. This is an exponential equation, so what you do, you log both sides to eliminate exponentials, and the base should be the same as the base of the exponential, and x would be natural log of 1, and we know that log of any base of 1 is 0. This is back from the review. When was this? When did we do logs? From 4.4. If you remember, when we did those rules, right there. Rule number 3. And if I take this equation, I notice that this is exponentials. The bases are the same. That means the powers must be equal. Cross multiply. Oops. If I cross multiply, I'll get x to equal -2. And there it is. So something that does come up, and you would need to solve it every now and then. Number 44 says the demand function for a product is given by, this is lowercase p for price, x is the number of units, price per unit, correct. So p is dollars and x is number of units. What price will yield the maximum revenue? If we recall, revenue is the number of units times the price. Revenue is x times 73 e to the negative 0.000025x. Revenue is 73x e to some power. I want to find a maximum of anything out there. How do we do it? We've done this too many times. We take a derivative. 73 is a constant. The product rule, derivative of the first times the second. How many zeros? 1, 2, 3, 4. Yeah. Plus the first times derivative of the exponential. That's the exponential itself. Times the derivative of the power, which is negative 0.000025. And I want to know, where does this derivative equal to 0, or where does it not exist? Well, let's see. If I factor that, if I factor out e to the negative 0.000025 x, 73 is multiplied by both, that will be 1 minus 0.000025x, right? So, where's this undefined nowhere? Where does this equal 0? This can never equal 0. So it has to be that 1 minus 0.000025x equals 0. Move that 1 over and divide. And if I get my calculator out, I'm looking for 1 divided by 0.000025, 40,000. If I do my testing, there is R prime, there's R, 40,000. And if I take a point to the left, let's say I take 1, this is always positive. Exponentials are, if I put a 1 right there, 1 minus 0.00025 is positive. And if I pick a point to the right, let's say 45,000, if I plug that in there, this is always positive. If I take 1 minus 0.00025 times 45,000, for example, a point to the right of 40,000, I'll get a negative. That's all I care about. So we have a maximum when x is 40,000 units. That's part A. To go for part B, I need to put some space. It's asking, what is the maximum revenue? Well, remember, the revenue function is right there. So if x equals 40,000, the revenue of 40,000 units is 73 times 40,000 times e to the negative 0.000025 times 40,000. And that would be how many dollars? I'll get my calculator out again. And 73 times 73 times 40,000 times, making sure I have enough zeros, e to the negative 0.000025 times 40,000. And I'm getting 1074. That's 1,074,207.97 cents. So that is $1,074,207.97. And there's our homework for this section.